computer is astonishingly fast and astonishingly literal. It cannot guess, improvise, or read your mind. To solve any problem, you must first break it into a precise, ordered list of unambiguous steps. That recipe is what we call an algorithm. But how do you turn a vague, tangled problem into clean steps in the first place? And once you have them, how do you make sure they actually work? That is the craft of algorithm design, and it starts with a way of thinking. First, decomposition. Break a big, scary problem into small, solvable pieces. A game is just input, rules, graphics, and scoring, each tackled on its own. Solve the little parts and the whole assembles itself. Then abstraction. Strip away the detail that doesn't matter. A subway map ignores real distances and streets, keeping only the stops and lines you actually need. And pattern recognition spots where a solution you already have fits a new problem too. We capture algorithms three ways. A floatchart draws the logic as boxes and arrows, with diamonds for decisions. Pseudocode writes it in structured, language-neutral English. Both say the same thing: one you see, one you read. And to check an algorithm really works, we use a trace table. We step through line by line, writing down every variable's value at each moment. If the final numbers are right, the logic is sound. If not, the table shows exactly where it broke. To find a value, the simplest way is linear search. Start at the first item and check each one in turn until you find it or run out. It always works, but in a list of a million, you might check all million. Slow, but reliable. But if the list is sorted, binary search is dramatically faster. Look at the middle. Too high, throw away the whole upper half. Too low, throw away the lower half. Each check halves what's left, so a million items take just 20 checks, not a million. Binary search needs sorted data, so how do we sort? Bubble sort is the classic. Compare each pair of neighbors, and if they are in the wrong order, swap them. The largest value bubbles up to the end on each pass through the list. Repeat the passes until a whole pass makes no swaps, and the list is sorted. Insertion sort takes a different route, building a sorted section one card at a time, like arranging a hand of cards. Different methods, the same tidy result. It starts with computational thinking. Decompose a problem into pieces, abstract away the detail that doesn't matter, and recognize patterns you can reuse. Turn the tangle into clear, ordered steps before you write a single line. Express those steps as a flowchart or pseudocode, and check them with a trace table that follows every variable. And know the standard algorithms: how to search a list and how to sort one. Linear search checks each item. Binary search halves a sorted list for huge speed. Bubble and insertion sort both put data in order, the groundwork that makes fast searching possible. How we measure an algorithm's efficiency formally comes later.